In this video, we're going to look at the reaction rate part of the first year syllabus, which is also called rates of reaction and sometimes called reaction kinetics. So in this topic, we're going to look at, first of all, some revision topics, which are collision theory and how to measure rate of reaction. And then we're going to look at Boltzmann distribution curves, which you would not have met at GCSE. And then finally, we're going to focus on one of the factors that affect rate of reaction, which is catalysts. Okay, so what is simple collision theory or collision theory? Well, it's very simple. Hopefully it's obvious that when reactants react together, their particles must meet up and therefore they must collide. Not only must they collide with sufficient energy, with enough energy to break bonds in the reactants so that the atoms will form a activated complex, and then the atoms rearrange and new bonds are formed to form the final products. Now, even if they don't react and they bounce off each other, the reactant particles may have subsequent collisions with other particles in the reactant mixture. And in those subsequent collisions, energy would be transferred between particles, and some particles in those collisions will gain enough energy to react. The minimum amount of energy for particles to collide with each other to cause a reaction is called the activation energy, and we already know this from looking at enthalpy profiles. And these collisions that exceed the activation energy and lead to a reaction are called successful collisions. So the more frequent the collisions, the more likely successful collisions will occur in a given time. So the frequency of successful collisions will increase. So even if only a small proportion of collisions are successful, but we somehow increase the number of collisions in a given time. Now I'll talk about some of the factors that will influence the number of collisions in a given time a bit later on. The rate of conversion of reactants to products, or the rate of reaction, will also increase. So what factors then will increase the frequency of collisions and therefore lead to the frequency of successful collisions increasing and therefore causing the rate of reaction to increase? Well, the first one is temperature. An increase in temperature would increase the rate of all reactions, because the increased temperature means that the particles will have more energy and therefore will collide more frequently with each other because they've been moving faster and more likely to collide with each other. And also their collisions will be more energetic and therefore more likely to be able to exceed the activation energy needed for the reaction to occur. Another factor that increases the frequency of collisions of particles in a reaction is the concentration of the reactants, and this only affects reactants which are in solutions, as you can't have concentrations of solids. Another factor that affects the frequency of collisions of particles is pressure, and this applies for gases only. The pressure of a gas effectively is the same as the concentration of a solution, as if there are more particles in a given volume for a gas, there'd be greater pressure, whereas more particles in a given volume for a solution would be greater concentration. So in terms of collision theory, they have the same effect. Whether we are increasing the concentration of solutions or increasing the pressure of gases, more particles of reactants in a given volume will mean that the particles will be closer together and therefore more likely to collide together in a given time, so the frequency of collisions would increase with increasing concentration and increasing pressure. Surface area of a solid will also affect the frequency of collision of a solid reactant. So the larger the surface area of the solid, the more frequent the particles could be in contact with other reactant particles. So often this would be particles in a solution. So the larger surface area of a solid in a solution, the more contact of the particles in the solution will have with the particles of the solid. And if we have a gas reacting with a solid, the larger the surface area of the solid, the more likely those particles of gas will collide with the surface of the solid, and so the frequency of collisions should also increase. When I used to teach these to GCSE students in year 11, I used to use the analogy of students go to a end of year ball. So for example, I talk about concentration of reactants as if we had the start of the evening and there are very few people at the ball, and this ball is in a big tented gazebo, and at the beginning there's very few people on the dance floor in this gazebo, so there's very little chance of them colliding and reacting. So later on, as the evening progresses, more and more people join the party and join the dance floor. So the concentration of the people are higher, and as they dance around, they're more likely to collide with each other and react. So the temperature is a bit like how fast the people are dancing on the dance floor. So at some stage in the evening, the DJ is playing a bit of a slow song and the people are dancing a bit too slowly, so they don't really collide very often and meet up and join up. So the DJ decides to liven up the party a bit and put on a higher beats per minute record that goes dush, 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 like a rave record. So the people are now dancing really, really fast and will collide with each other much more likely. With surface area of solids, I talk about a group of friends dancing very close together because they're very tightly knit and they wouldn't mix with anyone else. So the potential partners who want to get to the middle of that group will not be able to get into reacting with the people in the middle of the group that huddled up together to dance together. So what happens to increase the surface area? So maybe later on in the evening, that big group of friends will have an argument and they break apart into two separate groups. So now there is more surface area of people on the outskirts of these two groups, which the other people could collide with and meet up and react. And finally, with the pressure, very late in the evening, there's a huge storm brewing outside, and eventually the storm blows down the gazebo and collapses on the whole party and squeezes all the people together, and therefore the particles are much closer together, or the people much closer together, so therefore they will collide with each other and react. Earlier on, we talked about the fact that for a reaction to occur, the particles must not only just collide, they must collide with sufficient energy or have energy exceeding the activation energy for the reaction. So not only do we need to talk about the factors that affect the frequency of collisions, we need to look at also what factors increases the energy of the collisions as well. And out of these factors, there's only one that increases the energy of the collisions, and that's temperature. So the energy of collisions can only be increased by increasing temperature and nothing else. So increasing concentration or pressure or the surface area of the reactants will not increase the energy of the collisions, but will only increase the frequency of the collisions. Temperature therefore increases the frequency of collisions and the energy of the collisions. And also more of the particles have higher energy and therefore more likely to exceed the activation energy and to react. One final factor that we haven't mentioned that doesn't increase the frequency of collisions and also doesn't increase the energy of the collisions but will affect the rate of reaction is the effect of a catalyst. And the way a catalyst will work is it lowers the activation energy by providing an alternative reaction pathway for the reaction to occur. You must get the wording right in the exam to get all the marks. So a catalyst increases the rate of reaction by providing an alternative reaction pathway with lower activation energy. So therefore, you get a greater proportion of reactants that exceed the activation energy in a given time. And I will illustrate this when we talk about the Boltzmann distribution curves later on in the topic. Now, you don't need to explain how a catalyst works, but some solid catalysts works through a process called adsorption. So here's an example of the hydrogenation of ethene using a nickel catalyst. So this is an addition reaction where we add the hydrogen to the alkene. Now these are both gases, so the rate of collision between these gases will be very low because the particles are quite far apart. So to increase the rate of reaction, we need to increase the pressure, but it's very costly to increase the pressure too much. So to reduce the costs, we could use a catalyst, and what the catalyst does, it allows the reactant molecules to adsorb, to bind to the surface of the catalyst. And the adsorption process does two things. First of all, when the molecules adsorb or bind to the surface of the catalyst, it remains there for a bit of time. So if more of these molecules bind to the surface, it effectively increases the concentration of the reactants rather than the molecules being separate particles in a container of gas. They are now effectively concentrated on the surface of the catalyst. Not only that, in binding to the surface catalyst, it weakens some of the internal bonds of the molecules, so it lowers the activation energy to break these bonds, which is what we want to speed up the rate of reaction. So a greater proportion of those particles will exceed the activation energy and be able to react in a given time, so we increase the rate of reaction that way. So the other reactant can also bind to the surface of the catalyst, absorb to the surface of the catalyst and be very close to the other reactant. And in that process will weaken the bond between the two hydrogens, and also we start to form the bond between the hydrogen and the carbons on the original alkene. The bonds then form between the carbon and the hydrogens, and we break the bond between the two carbons, so the alkene disappears. We still got the final alkane from adsorbed to the surface of the catalyst, and the final stage is called desorption, where the molecules leaves the surface of the catalyst. So this is desorption. So in terms of the end of year ball or prom analogy, the solid catalyst is a bit like the bar at the prom or the ball, and that's where people hang around if they're not dancing around, but they can still meet up with somebody if someone comes along to get a drink. So the people will gather at the bar, and the concentration of those people will increase, and therefore they're more likely to meet up and react at the bar. And because of the alcohol at the bar, the activation energy is also lower there. So we covered some revision on collision theory, and what we do next is do a bit of revision on how we measure rates of reaction before we move on to Boltzmann distribution curves and catalysts.